Hello, my name is Donald Clark. I'm a machine learning engineer at Lucid and also an ex-NLP person, and I'm quite keen to get back into doing natural language processing again. And I did do a postdoc in the area of distributional semantics and compositionality in distributional semantics. And I'd like to get back to studying that again, but also I'd like to study just NLP in general, what's happened in the last 6 years or so since I've stopped doing it. And my idea is something a bit strange, which is to try and read papers for the first time while recording my reading of them and see if I can make sense of them in a short period of time. So I'm going to aim for around half an hour. We'll see how far we go. And the idea is to try and see if I can get some kind of vague understanding of the paper within half an hour. Let's see how it goes. So this paper is one by Marnoosh, who I happen to know, and the first author is Sanjay Ramgoolam, who I don't know. But I worked with Marnoosh, well, not directly, but we worked on the joint project when I was doing my postdoc, so I know a little bit of background around the area, but I think there's going to be quite a lot of maths and physics here, which I may not be familiar with. But we'll see how we go. But I'm interested in it because it relates to my research area. So, Gaussianity, typicality, and matrix distributional semantics. Sounds a bit scary, doesn't it? Constructions in type-driven compositional distributional semantics associate large collections of matrices of size D to linguistic corpora. Okay, so what that's saying is that for every word, you're going to get a matrix, I think. And that matrix is going to represent something about the meaning of the word, including how it composes with other words. So that when you compose those words, the composition, so if you've got a matrix for black and a matrix for cat, and you compose those two words together to get black cat, then the matrix for black and the matrix for cat compose such you get a new matrix, which somehow represents the meaning of black cat. And we developed the proposal of analysing statistical characteristics of this data in the framework of permutation invariant matrix models. Okay, so I don't know anything about that particular framework. The observables in this framework are permutation invariant polynomial functions of the matrix entries, which correspond to directed graphs. Sounds interesting. Using the general 13-parameter permutation invariant Gaussian matrix models recently solved, we find, using a dataset of matrices constructed via standard techniques in distributional semantics, that the expectation values of a large class of cubic and quartic observables show high Gaussianity at levels between 90 to 99%. Well, I have no idea what that means. Hopefully it'll become clear when I read the paper. Beyond expectation values, which are averages over words, the dataset allows the computation of standard deviations for each observable, which can be viewed as a measure of typicality for each observable. There is a wide range of magnitudes in the measures of typicality. The permutation invariant matrix models, considered as functions of random couplings, give a very good prediction of the magnitude of the typicality for different observables. No idea what any of that means. We find evidence that observables with similar matrix model characteristics of Gaussianity and typicality also have high degrees of correlation between the ranked lists of words associated to these observables. Okay, well, hopefully some of this is going to become clear. I'm going to load up the next page. And let's see what we've got. Some contents. Okay, this is quite a big paper then. A research program, Linguistic Matrix Theory, of understanding the characteristics of randomness in natural language, specifically in matrix tensor datasets arising from type-driven composition and distributional semantics, using the framework of random matrix tensor theories, was initiated in 1. So, I don't know what 1 is. Maybe I can load up the paper quickly and have a quick check what that is. Yeah, it is a big paper, this one. So 1 is Kartsaklis, Ramgoolam and Sadrzadeh again, Linguistic Matrix Theory. Okay, this is an archive paper from 2017. So it seems like we might need to have some background in that. Hopefully we can manage without that. Let's see how we go. Understanding the characteristics of randomness in natural language, specifically in matrix tensor datasets arising from type-driven compositional and distributional semantics. Okay, well, I know about type-driven compositional distributional semantics, so that's Bob Cooker's program. So Bob Cooker's at Oxford, and he's come up, and he, together with Stephen Clark and Marinucci, came up with this type-driven compositional and distributional semantics. Using the framework of random matrix tensor theories. So I'm vaguely familiar with random matrices from non-commutative probability theory, but it'll be interesting to see how those connect. Okay, distributional or vector space models of meaning in natural language semantics argue that meanings of words are representable by the context in which they often occur. Okay, so this is old hat for me. So this is the kind of standard distributional semantics stuff. We can probably skip over this, but basically the idea is that you can build up vectors of words based on by looking at their contexts in large amounts of text. Let's get the next page up. So there's a bit about needing to take into account grammatical structure, and I think that is all going to be fairly standard stuff. Type-driven distributional models of meaning start from a type-driven analysis of grammar, assign a compositional vector semantics to natural language construction. So the idea here is that the grammar tells you how the vectors for individual words compose. So here we've got, if we assign the vector space n to the type n for noun, and the vector space s to the type s for sentences, then adjectives and transitive verbs and verb phrases that only have one argument become elements of the tensor spaces n tensor n and n tensor s, respectively. And these are represented as matrices. Transitive and ditransitive verbs have 2 and 3 arguments each. They become elements of the tensor spaces n tensor s, and n tensor s, and represented as cubes and hypercubes, respectively. So I have an issue with this, which is the assumption of linearity that is made, because, well, it's possible that you can represent meaning and assume linearity, but you lose certain nice properties of the vector space of how the meanings relate to one another. If you do that, if you want to talk about entailment between phrases, for example, then you can lose some nice properties. But anyway, this is their framework, and it works for them. So let's continue going. When a word of the functional type composes with a word with an atomic type, the composition is represented by the application of the corresponding linear-multilinear map with the vector of the atomic word. As an example, consider the distributional meaning of, I think this is going to be red herring. Let's get the next page up. Oh, did I get the same one again? Where's it gone? Is it going behind here? Try again. Ah, I see those pages are 0 bytes. 1 minute. Try a different approach. So we've got cat, red cat, which becomes a result of the matrix multiplication of the matrix of red and vector of cat. Okay, so you've got a matrix red, so the matrix operates on a vector space of nouns and gives you back another vector in the space of nouns. and you obtain the matrix of red times the vector for cat and the meaning of red cat. Similarly, denoting the meaning of snore by a matrix for snore in the space of n tensor S, you obtain m snore times v cats as the meaning of cat's snore. So it looks like the sentence space is a vector, is in the space of vectors, so a single dimensional space. And when you apply snore to your vector for cat, so snore is an intransitive verb. So you end up with a sentence cat snore in the space of sentences. And the meaning of cats like fish means you've got a three-dimensional tensor for like, which was it's a transitive verb, and you operate that on fish and cats. Okay, so this is fairly straightforward, I think. You've just got tensors that operate on vectors. I have an issue with this whole approach, but let's ignore that for now. Okay, so the collection of matrices associated to adjectives and intransitive verbs of a corpus have large matrix sizes ranging from 100 up to 10,000 and to 40,000, e.g. to the original work of 13 for the higher dimensions and the sequel work of 14 for the lower ones. While the AI-inspired tasks are focused on extracting linguistic structure, e.g. word similarity from these matrices, such a large collection inevitably has elements of randomness. Any corpus is a finite, even if large, sample select from everything written in a language. The experience of random matrix theory has indeed shown that the patterns in the distribution of energy eigenvalues of complex nuclei also occur in a wide variety of complex systems. Well, that's interesting, but I don't know how we can extrapolate from that. So, in the linguistic matrix theory program of one of the first steps was to identify the appropriate type of symmetry. Here it was useful to consider the kinds of mathematical expressions which are used in distributional semantics to extract the meaning encoded in words. So we've got d dimensions for our vectors, and we're using the symmetric group SD because we're talking about permutations of d objects. We're considering matrix models with SD symmetry. Polynomial functions of matrix variables mij, which are SD invariant, have an elegant classification in terms of polynomials labelled by directed graphs. The degree of the polynomial is the number of edges in the graph. The number of nodes is unconstrained. There are two graphs at linear order, each associated with a permutation invariant polynomial. Oh, I'm getting a bit lost now. Okay. Hopefully this will become clear with examples. Let me get the next page. Okay, so the degree of the polynomial is the number of edges in the graph. The number of nodes is unconstrained. There are two graphs at linear order. Okay, I don't know what any of this means. A general permutation invariant linear function is the sum of these two polynomials with arbitrary coefficients. We restrict these linear coefficients to be real numbers, μ1 and μ2. Okay, well, at least we're dealing with real numbers. That's grateful for small mercies. There are 11 independent quadratic functions. As a simple toy model, we considered 3 quadratic polynomials with 3 associated coefficients, λ1, λ2, and λ3. Okay, so we've got a toy example. 3 quadratic polynomials. Okay. We defined a function S μ1, μ2, λ1, λ2, λ3, and considered a probability distribution defined by the partition function. Given any permutation invariant polynomial, which we will henceforth refer to as... Okay, so we've got a partition function defining a probability distribution. I'm not quite sure what the point of any of this is. Gotten a bit lost, I'm afraid. Let's go on to the next page and see if that helps. Okay, so this gives us a theoretical expectation value. Okay, so we've got a theoretical expectation value, which I don't think is going to bias very much in terms of understanding this paper. And the expectation values of the linear and quadratic observables are expressible as simple functions with mu a and lambda I. In order to match these probability distributions with experimental data, experimental expectation values for these 5 observables. Save the words. Oh, this isn't making any sense to me. I don't understand why we're doing this. Let's keep going. All right, let's see the next page. Okay, so here's the next page. I'm going to stop after these 2 paragraphs, I think, because I don't think I'm going to get very far with this paper without being a researcher in this field. I think I'm probably not going to get much out of it. But it is useful at this point to discuss our investigations of Gaussianity in language in the broader context of studying statistical aspects of language and of applications of matrix models in physics. The 2 central elements of the program initiated in 1, again, are Gaussianity and permutation symmetry. It is worthwhile discussing a potential objection to Gaussianity in linguistics, Zipf's flaw. So Zipf's flaw is the observation that in corpora of natural language, the frequency of a word is inversely proportional to its rank. So this is the way that you get these rare words that are actually very common. So it's this power law where if you look at a large amount of text, so say you look at 1 million words and you find a certain number of words that occur only once in those 1 million words, chances are if you add another million, look at 2 million words, you're going to find roughly twice as many words that only occur once. So those words aren't going away, essentially. So there's a lot of very rare words. Power law is, of course, nothing like a Gaussian. So a quick argument is that Gaussians are not what one typically gets in the statistics of linguistic corpora. So where does that leave us? I don't know. Since the 1990s, started from the works of those 3 papers, matrix theories have seen an explosion of applications in theoretical physics. Present application of matrix models to language can be viewed as the explanation of another instance of emergence from matrix theory. In the present case, the emergence is that of the universal aspects of randomness in natural language from the mathematics of matrix theory. One of the lessons from the applications of matrix model engaged string duality is that the validity of Gaussianity or approximate Gaussianity often needs to be carefully delineated in a complex system. The lesson is that the phenomena described in matrix theories are rich and diverse, with Gaussianities emerging from the identification of the appropriate observables. Okay, I'm afraid this still isn't making sense to me. Again, I think I'd need to be an expert in these random matrices to really understand what's going on here. It's a pity because it seems interesting, but I don't even understand the motivation for the paper yet, so I'm struggling somewhat. Never mind, it's been an interesting experiment in live reading of a paper. I think I might choose a paper that's a little bit less challenging next time. Anyway, I hope you managed to get something out of this, hopefully more than I did, and I might try this again. So I look forward to seeing you there. Thank you. Bye.